Okay, so if you remember in our previous video, we provided a very intuitive derivation for the formula of the arc length of a curve, in this case y equals f of x, between x equals a and x equals b. So our derivation was very intuitive. In this video, we want to provide a more rigorous derivation of the formula for the arc length of a curve between 2 points. The reasoning is the same, we'll be a little bit more rigorous with our derivation. So again, the intuition is this: cover the curve with short line segments, add the length of each line segment together, you'll have an approximate length for the curve, and as you let your line segments shrink to 0 in length, in the limit you will get the exact length of the curve. So let's now find, so if you imagine now what you have is essentially a partition of the interval, right, for each endpoint of the line segment. So you form your partition, and you're asking very simply for each interval, what is the length of the corresponding line segment, right? So interval 1, first line segment, interval 2, second line segment, and so forth. So all we have to do is find, for any given interval, the formula for the length of the corresponding line segment. So suppose we look at an arbitrary line segment, right? There's the first one, second one, third one, up to the last one, the nth one. Let's pick an arbitrary one. So the ith segment. So this would be I equals 1, I equals 2, I equals 3, and so forth. Suppose this is the ith one. So xi is our right endpoint. Our left endpoint is xi minus 1. Of course, the length of the interval, or the width, we always form an even partition, so all of the intervals, even though my picture is a little crooked, should have the same length. So our delta x, as always, is the change in x, the width of the interval, the larger x value, right endpoint, minus the smaller x value, left endpoint. And now we ask, well, okay, so over this interval, what is the corresponding length of the line segment? Well, again, we can form a right triangle. So we have the width of our base will always be the same, delta x for each interval. This is delta x. Now the height will change from interval to interval. It may be different, so I'll call this delta yi. And I really want to emphasize this. No matter what I is, whether I is 1, the first interval, I is 2, interval 2, and so forth, the width is always delta x, so it does not depend on I. But as you go, you can see from the picture, from one segment to the other, the height will vary. So it varies, it depends on the interval. So delta y depends on I, that's why we write delta yi. And the same thing for the length of our line segment. You can see that as you move from one interval to the next, the segments won't always be of the same length. So we'll denote this length by delta si, the length of the ith segment. And we'd like to express this in terms of delta x and delta yi. But we also want to express delta yi in terms of possibly delta x, and of course, some point between the interval. Well, if you think of it here, well, naturally, a change in y is a larger y value, and here the y value is f of xi, minus the smaller y value, and at this point, the y value is f of xi minus 1. So this is a change in y for the ith interval. But if you look here, we have f of xi minus f of xi minus 1. We can now apply the mean value theorem. So a change in y will be the derivative at some point inside the interval xi minus 1 to xi. Now this point is any point between xi minus 1 and xi, so it could be here, we don't know. But it has to be some point between these two values, times, of course, the right-hand point, xi, minus the left-hand point, xi minus 1. But all this is, of course, is delta x, the width of the interval, which is always the same. So we are left in the end with the derivative of our function at some point between xi minus 1 and xi times the width of the interval, delta x. And now we can express, using Pythagoras' theorem, the length of the i segment as a function of delta x, f prime, and delta x. So let's see what comes out. So let's apply Pythagoras' theorem. So the change in length over the ith interval squared is our hypotenuse squared, is of course the base squared, delta x squared, plus the height squared, delta yi squared. And now we'll replace our delta yi by the derivative at xi star delta x. And of course we're squaring the whole thing, so we'll have the derivative squared times delta x squared. The derivative all squared, delta x all squared. And once again, we have a common factor of delta x squared, so we can factor it on the right. That leaves us with 1 plus the derivative at the point xi star squared times delta x squared. We want not delta si squared, but delta si. As everything on both sides is positive, take the square root on both sides. And so what are we left with? Well, delta si is the square root of this expression, which is the root of the first term times the root of the second. So square root of 1 plus the derivative of the function xi star squared times, but the root of delta x squared, as delta x is positive, is simply delta x. And now we're ready to go. We are saying, okay, the length of the ith segment is given by this expression. So let me just rewrite it here. This is the length of just one line segment. If we want an approximate length of our curve, we have to add the length of each line segment. So we have to sum. And we're summing as I goes from the first line segment up to the nth line segment. But of course we know that this will give us an approximate length, right? If you add the length of these line segments, you will not get the exact length of the curve. Only as n goes to infinity, the number of line segments goes to infinity, they will become shorter and shorter and shorter, and in the limit you will get the approximate length of the curve. So to get the exact length, we have to let n, the number of line segments, approach infinity. And once we do this, then in the limit we get the exact length of the curve. But if you notice now, you say, okay, this looks very unpleasant, right? Evaluate the sum, take the limit as n goes to infinity, and you'll get the exact length of the curve. But this is the limit of a Riemann sum, right? This is the limit as n goes to infinity, summation from 1 to n. Now the function is the square root of 1 plus the derivative squared times the change in x. And so you see for every interval, for the first, second, third, and so forth, we evaluate this function at a given point, xi star, inside the interval. This is by definition the Riemann sum, well, the limit of the Riemann sum that corresponds to the definite integral from a to b of the function the square root of 1 plus the derivative squared and of course in the limit delta x shrinks to 0 and becomes dx. So there you have it. And this is now a more rigorous derivation of the formula for the arc length of a curve. Find the change in y over the ith interval, apply the mean value theorem, Use Pythagoras' theorem to find the length of the corresponding line segment over the ith interval, and you find such a formula. If you add up all of the lengths of these short line segments, you have an approximate length of the curve, and as you let the number of line segments approach infinity, you get the exact length of the curve, and of course what we had was the limit of a Riemann sum over the interval from a to b of the function square root of 1 plus the derivative of the function squared dx. And that's it. So in our next videos, we'll consider examples of how we can apply this formula to find the arc length of a curve given explicitly.